Hello students, welcome to AIMS-JEE online classes. This is a chemistry session. Here we are discussing about the chapter chemical bonding. In this session we are going to say about valency shell electron pair repulsion theory, which we call commonly as Vsper theory. So it's abbreviated as valency shell electron pair repulsion theory. This explains the geometry of the molecules. Okay, let us say about this theory today. Valency shell electron pair repulsion model of molecular shapes is a simple extension to Lewis ideas and is surprisingly successful for predicting the shapes of the polyatomic molecules. Okay, this valence shell electron pair repulsion theory is just simple extension to Lewis dot ideas. Okay, based upon those only these prediction of molecular structures were observed in valence shell electron pair repulsion theory, and here it is succeeded in predicting the shapes of the molecules on based on certain rules for most of the polyatomic molecules. Sedgwick and Powell proposed that for molecules and ions which have only single bonds, an approximate shape can be predicted from the number of electron pairs in the valence shell of the central atom. Okay, these two scientists, they have proposed certain ideas for predicting the shapes of the molecules which are having only single bonds, and based upon the number of electron pairs present on the valence shell of the central atom, the molecular shapes are predicted. The outer shell of the central atom of a molecule may contain one or more bond pairs of electrons and also one or more lone pairs of electrons also. For example, if you say ammonia molecule, what is the central atom in ammonia molecule? As you know, it is nitrogen. Observe here nitrogen, it is bonded with 3 hydrogen atoms with 3 covalent bonds, isn't it? Now, the pair of electrons which are participating in the bond formation are called as bond pair of electrons. This is one bond pair, this is one bond pair, and it is one bond pair. These three are called bond pairs of electrons. And if you say on the nitrogen, there is one more pair of electrons which is not participated in the bond formation. It is present in the valence shell but not participated in the bond formation, and hence that pair of electrons present in the valence shell without participating in the bond formation is called lone pair. So in this way, in a polyatomic molecule, the central atom may have one or more bond pairs of electrons and also one or more lone pairs of electrons also. Okay, the pairs, bond pairs and lone pairs of electrons are expected as equivalent, since all electron pairs take up some space and repel each other, isn't it? All the pairs of electrons are considered as equivalent and they repel each other because of repulsions. So repulsion is minimized if the electron pairs are oriented in space as far apart as possible. So if they are oriented in the space as far as possible, then the repulsions between these electron pairs will be minimized. In that way, these electron pairs will be arranged in the space. So based upon this concept, the shape of the molecule is predicted. So Gillespie and Niall improved the theory to predict and explain molecular shapes and bond angles of the molecules more exactly. Okay, these two scientists, they have improved this theory and they have tried to given information or instructions to predict and explain the molecular shapes of the most of the and even bond angles also more exactly. Now let us see how they have improved. Let us see those postulates of this valence shell electron pair repulsion theory, based on which we can predict the shape of the geometry or geometry of the molecule and even bond angles in the molecule also. Let us see those postulates. One of them is the shape of the molecule is determined by repulsions between the electron pairs present in the valence shell of the central atom. So based upon the electron pairs present on the central atom of a molecule, the shape or geometry of the molecule is determined, because these electron pairs present on the central atom in a molecule, they repel each other. So to overcome these repulsions, they will be oriented in the space as far as possible from one to another. So based upon this concept, the geometry or shape of that molecule is determined. A lone pair of electrons take up more space around the central atom than a bond pair. This is because the lone pair is attracted to only one nucleus, whereas the bond pair is shared between two nuclei. Because of this reason, a lone pair will be repelling the other pairs of electrons greater, and it takes up more space around the central atom. Okay, because this lone pair of electrons is attracted to only one nucleus, that is the central atom. Whereas if you see the bond pair of electrons, they are connected to two nuclei. One it is central atom, another is another atom which is connected to that. In this way, bond pair is in connection with the two nuclei, or attracted to two nuclei of the atoms. But whereas lone pair is connected or attracted to only one nuclei, that is of central atoms. In this way, lone pair will be having more effect, and it repels the remaining pairs of electrons greater, and it takes up more space around the central atom. Okay, this also to be considered while predicting the shapes of the molecules. So if it follows that repulsion between two lone pairs is greater than repulsion between a lone pair and a bond pair. Okay, the repulsion between two lone pairs will be greater than the repulsion between a lone pair and bond pair, which is in turn greater than repulsion between two bond pairs. Okay, the repulsion between a lone pair and a bond pair is greater than the repulsion between two bond pairs. Now we can say the order of repulsions between the electron pairs as shown here. The repulsion between two lone pairs is much greater than the repulsion between bond pair and lone pair, which in turn greater than the repulsion between two bond pairs. So based upon this, the shape of the molecule can be predicted. So lone pairs, if there are on the central atom, they take up the more space. They repel the remaining pairs of electrons more. Okay. The presence of lone pairs on the central atom causes slight distortion of the bond angles from the ideal shape. If there are only bond pairs, then the shape can be predicted ideally. But if there are lone pairs also along with the bond pairs on the central atom, these will distort the shape of the molecule. There will be slight change. There will be slight distortion of the bond angle from the ideal shape. If the angle between a lone pair and the central atom and a bond pair is increased, it follows that the actual bond angle between the atoms must be decreased. So if there is a lone pair of electrons, then the bond pair will be less, the bond angle will be less than the expected, than the ideal case. Okay. The magnitude of repulsion between bonding pairs of electrons depends on the electronegativity difference between the central atom and other atoms. So in the earlier case we have seen the extent of repulsion is greater with lone pairs of electrons than bond pairs. So lone pair repulsion is greater than lone pair bond pair repulsion, and which is greater than bond pair repulsion. And again, now among the bond pairs, the magnitude of repulsion between bonding pairs of electrons depends upon the electronegativity difference between the central atom and the other atoms. So based upon that also, the extent of repulsion between the bond pairs varies. Double bonds cause more repulsion than single bonds, and triple bonds cause more repulsion than double bonds. Okay, this is one order we have to consider while predicting the shape of the molecule. A single bond has less repulsion than a double bond. A double bond has less repulsion than a triple bond. So if there is a triple bond, this will repel the remaining pairs of electrons greater than double bonds and single bonds. Okay. Multiple bonds between two atoms count the same as single bond in predicting the shape. Okay, in between two atoms, if there are more than one bond or you can say if there are double bonds or triple bonds between two atoms, those all three bonds or double bonds will be considered as a single bond while predicting the shape, because it does not matter how many electron pairs present in each direction. So that is considered as one bond while predicting the shape. Okay. Now, in studying molecular geometry, it is convenient to divide different molecules into two categories. Okay. To understand easily the molecular geometry, it is better to divide all kinds of molecules into two categories. One of them is molecules in which the central atom has no lone pairs. Means the central atom will be with only one or more bond pairs of electrons only without lone pairs. That is one kind. For example, molecules like beryllium chloride. If you observe in the beryllium chloride, beryllium is having two bond pairs of electrons in its valence shell, but there are no lone pairs of electrons. In the same way, BF3, boron trifluoride, in that also central atom boron has only three bond pairs of electrons, no lone pairs. In the same way, you can see the remaining molecules also like methane, CH4, PCl5 and SF6. In these all molecules, the central atoms are having only bond pairs of electrons but no lone pairs of electrons. So these all molecules, let us try to categorize as one kind. And the other kind is molecules in which the central atom has one or more lone pairs of electrons also along with bond pairs. For example, SO2, sulfur dioxide molecule. In this central atom is sulfur. It has two lone pairs of electrons and two bond pairs of electrons also. Sorry, one lone pair of electrons also, isn't it? So in this way, here the central atom in the sulfur dioxide molecule is having bond pairs of electrons and lone pairs of electrons also. If you observe ammonia molecule, in ammonia molecule central atom nitrogen has three bond pairs with three hydrogen atoms, one with each. At the same time, it has a lone pair of electrons also. In this way, these all molecules, water molecule, xenon tetrafluoride and PCl3, these all molecules will come under this category, in which molecules are having bond pairs of electrons and along with lone pairs of electrons also on their central atom. So by categorizing the molecule, all the molecules into these two types, let us try to understand the geometry. First, let us see the molecules which are having only bond pairs of electrons without lone pairs of electrons on their central atom. Let us try to predict their shapes and even bond angles also. First, let us see the molecule with only two bond pairs of electrons without lone pairs. If there are only two bond pairs on the central atom, then the geometry will be linear shape. Linear. And its shape will be like this model. Central atom is represented like this and two bond pairs will be arranged in the linear shape on the opposite sides. If they are in the linear shape, what will be the bond angle then? The bond angle will be 180 degrees. And now examples for the molecules having this linear shape with only two bond pairs, no lone pairs are CO2. See here, central atom C is connected with the two oxygen atoms. While predicting the shape, we are told to assume that multiple bonds are also as single bonds. Now this is one bond pair, this is one bond pair. Two bond pairs, no lone pairs on the central atom. Now these two will be arranged in the opposite direction in a linear shape. Now the bond angle will be 180 degrees. One more we can say, BeCl2, BeF2. In these all molecules also there are two bond pairs, no lone pairs. So those molecules also acquire this linear shape with 180 degrees bond angle. Next, let us see molecules with three bond pairs, no lone pairs. If there are three bond pairs on the central atom without any lone pairs, then the shape of the geometry of the molecule is expected as trigonal planar shape. Trigonal planar geometry. See the model like this it will be. Central atom is in center and three bond pairs are arranged in the space in the same plane in the trigonal planar shape. And then the bond angle will be 120 between any two bonds. Bond angle is said to be 120 degrees. An example for the molecules having this trigonal planar shape means with only three bond pairs, no lone pairs on the central atom. BCl3, BF3. In these molecules, the central atom boron has only three bond pairs. No lone pairs are present. Now these three bond pairs will be arranged in the space in the same plane with the trigonal planar shape with bond angle 120. Okay. Next, let us see the molecules with four bond pairs and no lone pairs on the central atom. Then the geometry is expected as tetrahedron shape. See, that will be represented like this in this model. Tetrahedron shape. Four bonds will be arranged in the equal distance from each other in the space. This shape is called tetrahedron shape. And here the bond angle is 109 degrees 28 minutes or 109.5 degrees, half of the minute. Okay, half of the degree it represents around. Now, the examples of the molecules having this tetrahedron shape, we can say as CCl4, CH4. These are all molecules in which the central atom has only four bond pairs and no lone pairs. Will come under this tetrahedron geometry. See here, CH4, carbon has four bond pairs. These all bond pairs are arranged in equal distances from one to another, and hence the shape is called tetrahedron shape, and bond angle there it is 109 degrees 28 minutes. Okay. Now let us see another one. The molecules with 5 bond pairs and no lone pairs. If there are only 5 bond pairs without lone pairs, then the shape of the geometry of the molecule is expected to be trigonal bipyramidal. So see the model how it is representing. So in this trigonal bipyramidal geometry, in the molecule central atom will be with 3 bonded pairs in the same plane with the trigonal planar shape, and one bond pair will be above the plane, another bond pair will be below the plane. So if you observe from the above the plane, it will be like a trigonal pyramidal shape, and below the plane also there is trigonal pyramidal shape. So total it is said to be trigonal bipyramidal shape. Understood? So the molecules with 5 bond pairs, no lone pairs will acquire the shape trigonal bipyramidal shape. And hence if you observe here, the bond which is above the plane, it will make a 90 degrees angle with the plane, and within the plane if you observe between any two bond pairs, the bond angle will be 120. So in this trigonal bipyramidal geometry there exists two kinds of bond angles. Above and below the plane there are two bond pairs. They make 90 degrees bond angle with the plane, and within the same plane there are 3 bond pairs. Among these any two bond pairs there exists 120 degrees because they are in the trigonal planar shape geometry. Okay, and examples for the molecules having this kind of geometry are PCl5, PF5. These all will come under the molecules with trigonal bipyramidal geometry. In this the central atom phosphorus is having 5 bond pairs, no lone pairs. Okay, 3 bond pairs are there along with the phosphorus in the same plane in the shape called trigonal planar shape, and there is 1 bond pair above the plane, 1 bond pair below the plane. If you observe from the above the plane, it will be like a trigonal pyramidal shape. if you see from the bottom of the plane, there is one more trigonal pyramidal shape. Altogether it is said to be trigonal bipyramidal shape. Okay. Next, the molecules with 6 bond pairs, no lone pairs. Then the geometry of the molecule is expected to be as octohedron with 8 sides. Octohedron. See the model of these molecules. The central atom is with along 4 more atoms or 4 bond pairs in the same plane, and there is one bond pair above the plane and one more bond pair below the plane. So from all the corners, if we observe, there exists 8 sides. That's why it is called octohedron. Octohedron shape. Here the bond angle will be between any 2 bond pairs, there will be 190 degrees. Okay. And the examples for the molecules having this kind of structure is SF6, sulfur hexafluoride it is called. In this molecule, the central atom sulfur has only 6 bond pairs, no lone pairs. So it acquires a geometry octohedron in which the bond angles are 90 degrees between any bond angle, any bonds. Next one, the molecule with 7 bond pairs, no lone pairs. Then the geometry is expected to be pentagonal bipyramidal shape. So it will be like this. Here 5 bond pairs are there in the same plane along with the central atom, and one bond pair is above the plane and one is below the plane. So 5 are there in the same plane. That is said to be pentagonal shape, and there is one bond above the plane. If you observe from the top, it will be like a pentagonal pyramidal shape, and from the bottom also pentagonal pyramidal shape is there. So overall it is said to be pentagonal bipyramidal shape with bond angles 90 and 72. Above and below the planes they make 90 degrees, and within the plane between any 2 bond pairs the bond angle will be 72 degrees. An example for the molecules or ions with this pentagonal bipyramidal shape are IF7, ZrF7 3- zirconium fluoride, heptafluoride ion. In this all, the central atom will be having 7 bond pairs, no lone pairs, and hence the molecule acquires pentagonal bipyramidal geometry. So these are the molecules with only bond pairs without lone pairs. Now let us see the second category of the molecules which we segregated. Those are the molecules with bond pairs and also one or more lone pairs on the central atom. Now first let us see the molecules with 2 bond pairs and one lone pair also. So if there are only 2 bond pairs, what will be the shape expected? Linear shape. But by the presence of one bond pair, the geometry will be distorted. Now geometry is said to be bent or angular shape. So model is like this. So instead of being linear with 2 bond pairs, because of the presence of lone pair, these will be distorted. Bond pairs will be pushed down. That's why the bond angle or the shape is said to be bent or angular, which we also say V shape. Okay. Now here the bond angle may vary from one molecule to another molecule, but in average it is said to be 119 degrees 3 minutes. Okay. Example for the molecules having this kind of geometry are sulfur dioxide. In the sulfur dioxide molecule, the central atom sulfur is connected with 2 oxygens. So the number of bonds between any 2 atoms are considered as 1 while predicting the shape. Now we can say here the sulfur is with 1 and 2 bond pairs and 1 lone pair. So the shape is said to be bent shape or linear shape. Okay. Now let us see one more kind. The molecules with 2 bond pairs and 2 lone pairs of electrons on the central atom. Then the shape is expected here also bent or angular. So this will be the geometry model. See, these two are these white connections representing bond pairs, and these two represent lone pairs. So because of the presence of these lone pairs, these bond pairs are repelled down. If there are no lone pairs, what will be the shape then? It will be linear. But because of this lone pairs, the shape is distorted and the bond pairs are pushed down. It acquires bent geometry or angular geometry, and here the bond angle is considered as 104 degrees 5 minutes. For example, the molecule with the bent shape or angular shape is a water molecule. In this central atom, oxygen is having two bond pairs and two lone pairs on its central atom oxygen, and hence the shape is bent or angular. One more, let us see here. Two bond pairs and three lone pairs. Now what will be the shape? Linear shape. This will be the model. See, because of the presence of three lone pairs, two bond pairs will come into one line. Linear shape they acquire. In the same line they come along with the central atom. Now three lone pairs will acquire a trigonal planar shape in one plane. Above and below the plane, these two bond pairs are acquiring linear shape. So while predicting the shape, we consider only bond pairs, remember that. Okay, now because of these three bond lone pairs, these two came to linear shape. As it is in the linear shape, what will be the bond angle? 180 degrees. An example for the molecules having this kind of structure are Xenon Difluoride. In the Xenon Difluoride molecule, xenon is with two bond pairs and three lone pairs of electrons. See here, three lone pairs acquired a planar geometry in the same plane along with the central atom. One bond is above the plane, another bond is below the plane. Now these two are in the linear geometry with the central atom. Right? Now let us see one more kind, the molecules with three bond pairs and one lone pair. Then the shape will be trigonal pyramidal shape. So this will be the shape. So if there are only three bond pairs, we expected the shape as planar, trigonal planar. But because of the presence of this lone pair, these bond pairs are pushed down. So they acquire a pyramidal shape with the trigonal. So trigonal pyramidal shape it is called. Here the bond angle will be around 107 degrees. An example for the molecule having such kind of geometry is ammonia. In NH3 molecule, central atom nitrogen has three bond pairs and one lone pair. So it acquired trigonal pyramidal geometry. Okay. Next, the molecule with three bond pairs and two lone pairs. Then the shape will be T shape. See the model here. This pink one representing central atom, and these white balls representing bonded atoms to the central atom. Now the shape is expected as T shape. The two lone pairs are above the T here. Okay, this shape is considered as T shape. And in this bond angle will be, here it will be 90 degrees, here it will be 180 degrees. Two bond angles are existing. An example for the molecule such kind of shape, that is T-shaped geometry, is chlorine trifluoride, ClF3. This, if you observe central atom, chlorine has three bond pairs and two lone pairs. So it acquires T-shaped geometry. Next, the molecule with four bond pairs and one lone pair. In what will be the shape? It is said to be seesaw geometry. See here, it is like seesaw. It is like strand and it is like seesaw, isn't it? It is said to be seesaw geometry, and one lone pair is taking the place above the plane here. Now, in this, the bond angle will be 120 and 90. So here the bond angle will be 90 degrees and here the bond angle will be 120 degrees. And the example for the molecules having this seesaw geometry is SF4, sulfur tetrafluoride. In this molecule, central atom sulfur is with 4 bond pairs and 1 lone pair of electrons on it. So it is acquiring seesaw shape. See here, it is a seesaw and it's a stand, isn't it? It is said to be seesaw geometry. Next, the molecule with 4 bond pairs and 2 lone pairs. Then the shape is said to be square planar geometry. This is a molecule model. So four bond pairs are there in the same plane along with the central atom, square planar shape, and above the plane and below the plane two lone pairs are acquiring their space. And here the bond angle within the plane, it is 90 degrees between any two bond pairs. And the example for this kind of molecules is xenon tetrafluoride. In this xenon tetrafluoride, central atom xenon is having two lone pairs and along with four bond pairs. Now here these four fluorine atoms or four bond pairs are in the same plane along with the xenon with the central atom. Above and below the plane, two lone pairs are taking their place. Okay, this geometry is said to be square planar geometry. Next, the molecule with the 5 bond pairs and 1 lone pair. Then the geometry is said to be square pyramidal. See the model. So here, so the 5 bond pairs, 4 are there in the same plane along with the central atom. One is above the plane. So up from the above the plane, if you observe, it is in the shape square pyramidal, and the lone pair is taking the bottom place. That's why it is said to be square pyramidal shape. Now the bond angle will be 90 and 180. So here with this, the bond angle for any atom in the same plane will be 90 degrees. Within the plane, the bond angle is said to be 180 degrees. And the molecules, for example, for this kind of geometry are ClF5, chlorine pentafluoride, contains 5 bond pairs and 1 lone pair on its central atom, chlorine. So it acquires a square pyramidal shape. Now let us see the molecule with 5 bond pairs and 2 lone pairs. Then the shape will be pentagonal planar shape. This is a molecule. There are 2 bond pairs on the central atom along with 5 bond pairs. 5 bond pairs will be in the same plane along the central atom. 2 lone pairs will take the place above and below the plane. This shape is said to be pentagonal planar shape. So here the bond angle will be 72 degrees between any two bonds. An example for the molecule for this kind of geometry, that is xenon pentafluoride ion. In this central atom, xenon is having 5 bond pairs and 2 lone pairs. So it is acquiring pentagonal planar geometry. Okay, this is about different kinds of molecules and their geometry. Thank you for watching our video. Please subscribe our YouTube channel AIMS Today for latest updates on recorded videos. And also visit our website aimstoday.in for another information regarding online classes, quizzes, live worksheets, activities, and even English and coding classes also.